Hi class, this is Dr. Martino. This is going to be a series of mini lectures on something called PV loops. So I normally do this in one big lecture, but we're going to break it down into 5 to 7 minute bits. And hopefully I've got a lot of extra slides, all of which I will put up um, on Schoology as soon as I'm done with this lecture. So let's talk about this thing called a PV loop. So the PV loop, pressure in millimeters of mercury, which is the way we measure blood pressure, is on the left axis. Volume in milliliters is on the x-axis. So the y-axis is pressure, the x-axis is volume. This particular loop here represents a basic normal left ventricular PV loop. So this is the amount of pressure and the amount of volume located in the left ventricle, which is the biggest, strongest chamber of the heart, and that's the one that pumps the blood to the rest of the body. So that's the most important chamber of the four. Let's just take a look at the different pieces here. So what you have here is what I like to tell students to think about here is you always start from this spot right here. Start from that spot. Okay, so whenever you're going to draw one of these or whenever you're going to think through one of these problems, that's the spot you think about. Okay, so start there. So you're going to move along this bottom curve here. And this bottom curve here is called the diastolic pressure curve. It represents the rough extent limit of diastolic pressure. Okay. This portion from here to here is called filling. All right, so that's when the chamber is filling. Now notice there is no time component here. This all happens during a time component, right? It's just that the time component isn't obvious here. When we get to Wigger's diagram, it will be obvious. So you're going to have to understand that this is happening over one heart cycle for the left chamber. So the heart, blood comes in through the right side of the heart, eventually gets to the left side of the heart and starts to fill the left chamber. So as it fills, not only does the volume of blood inside the chamber increase, but the pressure starts to increase too, right? So you have this pressure here that's increasing. Okay, so that by the time you've filled the chamber, the pressure that's in that chamber is about 15 millimeters of mercury, and it's about 140 mils of blood. Remember, this is different for every human being. This is just an example of a standard human being, right? 165 pound, 5'10" male, roughly is what we're talking about. Okay, when you get to this point here, that's called the end diastolic volume. Because during the filling stage of the heart, right, and the chambers, that's diastole. Diastole is the resting. Your heart is not pumping. So when it's not pumping, right, it is filling. So you get to the end of the filling, you're at the end of diastolic volume. What happens there is the valve that opened here to let the blood into the left chamber closes. The mitral valve closes. So now you're pumping against a closed chamber. The heart starts to squeeze, and you get an increase in pressure. Now, this pressure increase is called an isovolumic contraction or an isovolumic pressure change. That's because the heart is pumping against a resistance, an infinite resistance right now. And so iso meaning no change in length, just like an isometric contraction of a skeletal muscle, this is the equivalent in the heart. So you fill the chamber, pressure's going up, volume's going up. This valve closes. Now the heart starts to contract that chamber, the left chamber, and it's contracting and it's building up pressure. But there's no change in volume because the blood can't go anywhere. When it gets to this point here, right, it keeps going, and then it gets to this point here. Now, that point is roughly about 80 millimeters of mercury, give or take, 81 millimeters of mercury. And that point is the point at where the aortic valve opens. So you increase the internal pressure of the left chamber of the heart to exceed that of the valve pressure. The valve pressure is about 80 millimeters of mercury, so you get to 80.5, 81, and the valve opens. You get ejection, you get a peak pressure, and then the pressure starts to come back down. Remember, we're looking at the changes inside the heart. So when this valve opens, blood is going to the rest of the body through the arteries. What starts to happen is you have a continual increase in pressure after that valve opens, and then ultimately it will start to decrease. When you get to this point here, which is about 90 to 100 millimeters of mercury, the aortic valve closes, and then you get what is called an isovolumic relaxation. The heart muscle starts to relax, but there's no change in the pressure, in the volume, in the left chamber of the heart at this point. And so you started at about 75 mils, you went up to about 140 mils, you started at almost zero pressure, about 5 millimeters of mercury, you got to about 15 here, 80 millimeters of mercury here, about 120 millimeters of mercury here. You lost all of that fluid from the left chamber of the heart. You get to about 90 to 100 millimeters of mercury here. The aortic valve closes, and at 75 is where you stay for mils, and then you start the cycle all over again. This curve here, this straight line, represents something called the systolic pressure curve. So this is the limit. This is the limit of systolic pressure. So the PV loop has to reside between the diastolic and the systolic pressure curve under non-pathological conditions, right? This is not pathology. This is normal, basic physiology. So here's what you're going to do. I don't want to make this video too long. So what you have to do is you need to memorize all of these parts and make sure that you could draw a PV loop in about 2 to 3 minutes. So therefore, for an exam, I would ask you to be able to draw a normal PV loop from memory and then from there manipulate it, right? So this is not so much about the memorization, it's more about manipulating and understanding the mechanics of the heart. Okay, so this is an introduction to a PV loop. I'll have several more videos just on this. This seems to be an area that students seem to struggle with. And so I've broken it down into many smaller lectures. Please listen to the full sets of lectures, and I will talk to you soon. Take care.